Learning outcome 911. Given the Laplace transform of a function, calculate the initial and final values by both inversion and initial value theorem and final value theorem. There are two important theorems that you might have seen in an earlier class where you've used Laplace transforms that allow you to calculate the limits of a function at time 0 and time infinity for a time domain signal given only the Laplace transform of that signal. These are called the initial value theorem, quite often abbreviated IVT, and final value theorem, abbreviated FVT. Make sure that they're written correctly in your book because some books have a misprint on that. They're at the bottoms of table 9.1 and 9.3. The initial value theorem is x of 0 plus. We're looking at the value just after that initial time. And that's going to be the limit of s times x of s as s goes to infinity. The final value theorem is the limit as time goes to infinity x of t. This is x of infinity for short notation. And that's going to be the limit as s goes to 0 of s times x of s. Make sure you remember to multiply these by s. It won't work without that. And that's a mistake students quite often make, is they forget that s in their calculations, and they're so eager to rush through the problem. Let's work through 3 examples to illustrate this learning outcome. I'm giving you both the time signal and the Laplace transform, so you don't need to manually do the inversion. This time signal, x of t is 3 e to the minus 4t u of t minus 2 e to the minus t u of t, has a Laplace transform. X of s is 3 over s plus 4 plus negative 2 over s plus 1. This has the region of convergence of real part of s greater than negative 1. We want to know its initial value, the time signal's value at just after time 0. We can use the initial value theorem, which says to take our Laplace transform, multiply it by s, and then take the limit of that as s goes to infinity. This first term, we have the s's cancel, so we have a limit of 3. Second term, the s's cancel, we have a limit of negative 2. 3 minus 2 is 1. If we were to look at our time signal, at time 0, e to the 0 is 1, so this has the first term has a value of 3. At time 0, e to the 0 has a value of 1, so our second term has a value of negative 2. 3 minus 2 is 1. Let's look at this example, but if these two terms were multiplied out, which is quite often how you receive it if you're asked to invert it. We still apply the initial value theorem the same way. Now our function we type in looks a little bit different, but it's mathematically equivalent. We'll still multiply that s through. Now we have the s squared over s squared, which gives us a limit of 1 as s goes to infinity. A second example, this time, same function. This time, we want to look at what happens as time goes to infinity. We'll use our final value theorem. This says, then we substitute in our Laplace transform, multiply, and we need to see what happens as s goes to 0. The numerator will be 0. The denominator will be 4. 0 divided by 4 is well defined as 0. And for the second term, likewise, as the numerator is 0, the denominator is 1, so we get a 0 minus 0, which equals 0. And if we look at our two functions, both of them are decaying exponentials. So as time goes to infinity, both of those will go to 0. Let's look at this example also with our x of s multiplied out into a 1 ratio of fractions. We still apply the final value theorem. Take our s and multiply it by original transform function. Multiply the s through. Now as the limit goes to 0, the numerator is 0, the denominator is 4. which equals 0. Same result. Let's look at a third example. X to t is 3u of t. From table 9.2, property 2, the Laplace transform is 3 over s. The region of convergence is the real part of s greater than 0. We want to know what happens to this time function as time goes to infinity. Again, we'll use our final value theorem. We substitute in our transform, multiply, and the limit as s goes to 0 is 0 over 0, but we use L'Hopital's rule, that's 3 over 1, and therefore 3. If we look at our time signal, that's a time signal which is a step function, goes up to 3 at time 0, and continues at 3 until time is infinity.